So up next, we'll have Stella Ishitani Silva tell us about CNNs for exoplanet detection and photometric light curves for massive data surveys.
Yes. Hi, hello everyone. So my name is Stella, and I'm a NASA postdoctoral fellow at NASA Goddard, and I'm also a member of the Roman Galactic Exoplanet Survey team. And as they already said, I'm going to present about convolutional neural networks for exoplanet detection. So just to start, is this the one that passes? Okay, so as we know, our galaxy contains hundreds of billions of stars, and data suggests that we can, the exoplanets outcome all the number of stars, and there are a few exoplanet detection methods. So I'm going to talk a bit of the most popular one, the planetary transit, and then I'm going to mention also the gravitational microlensing. So I want to mention real quick why transit has all this high percentage, and this is mainly due to purpose-built space telescopes like Kepler that was retired and the ongoing tests. And in this presentation, I will also talk about gravitational microlensing, and gravitational microlensing will take center stage with the upcoming Roman Space Telescope. So Roma is going to be the first space mission that has as one of its primary goals the search for exoplanets with microlensing, and we expect to detect 1,000 more of them. But what challenge we have with this new telescope? So Roma stands as the top priority large space telescope mission, and its field of view is 200 times larger than Hubble wide field camera. So no other space telescope has this quality of data with this field of view. And because of this quality of data and this field of view, Roma will deliver hundreds of millions of precise light curves. And just to put into perspective, this is an infograph showing 30 years of Hubble, and this is only 5 years of Roma. So this is really huge. This is beneficial for science because it's gonna help us find rare events, and also it's gonna help us with statistical analysis. But it brings challenge, right? Because we have to now mine, process, and analyze all this data. So how can we guarantee that we prepare and that we are mining, we are finding the microlensing exoplanets event that we want? So neural networks can be an alternative for that. So this is a work that we did 2 years ago with planetary transit, so the other method that I was mentioning. We use a convolutional neural network to detect planetary transits in the TESS light curve. Just a quick review for people that are not familiar with the planetary transit method detection. Basically, when a planet passes in front of a star, it blocks part of the light. The subtle change that is less than 1% indicates that there is a presence of a planet. So we use this light curve with no pre-extraction features. So we are only using the flux of the light curve, and we knew a few confirmed transiting exoplanets, and we were able to detect 180 new exoplanet candidates. But what we learned from that was that CNNs, they can learn the prediction function, and they recognize features in light curves, and they do this very fast. They could do each light curve in milliseconds after trained. And another good insight from that is that we saw that light curves, they are like 1D image, which is a perfect case to be working with CNNs. So that's why we decided to use a similar method for gravitational microlensing. So nowadays, Rome is being assembled, and and ground-based telescopes are the one responsible for microlensing discoveries. We can see here in the animation, just to reveal what is gravitational microlensing, we see the light of a background star being amplified by two objects passing in front of it, a host star and a planet. And we can see here the anomaly due to the presence of the planet. Microlensing is kind of rare because we need some alignment. It's not periodic, and also it's very complex to model a binary lens model to millions of light curves. So we need a way to select what light curves we're gonna investigate. Nowadays, the selection methods, they look for magnified events and then they model single lens events. The problem of that is that it can miss multiple lens events, which is what we are looking for because we are looking for planets. So neural networks can be really a tool for that because we can train the neural network with the planetary event, which is what we want, and once trained is fast. So right now we are using, to prepare for Roman, we are using the MOA dataset. MOA was the first high cadence microlensing survey towards the galactic bulge. We have a 9-year of data with 2.4 million light curves. 23,000 of them has received human spectral labels, so somebody really saw it. And of them, 6,000 gravitational microlensing events. So real quick, our approach, we train our neural network and it was able to infer, again, in milliseconds, each light curve from the test set, give a confidence score. So a confidence score is a score of how confident the neural network is that there is a microlens event. We did cross-validation to have a complete list, and we combine this confidence score with a threshold. So the threshold works like that. If we want to focus on missing less events, so we would choose a lower threshold. If we want to focus on have less false positives, we're gonna have a larger threshold. And so this is our work so far. We want to improve it with simulations, but just to conclude, because my time is almost done, I want to highlight this graph here. So this is planet mass versus distance from the host star. And in red, we have Kepler. And we expect the blue one to be Roman. So we expect Roman to really complete the census of exoplanets that we have. And then we would have the most comprehensive fundamental data on how common planets of different masses are at a broad range of optical separations. And we need this data to test planet formation theories, planet evolution theories. But for that, we also have to guarantee that we're finding the planets. And neural networks can help us detecting microlensing exoplanets. Thank you.
Okay, thanks. If we have one really quick question in New York, we'll take it. And otherwise, please put your questions into Slack. Okay, well, let's thank Stella again, and then let's go to our next speaker.
We have a short question in Paris. Is that possible?
Okay, yeah, sure. Go ahead.
Great. Thanks. Just wondering, so microlensing is very, very short time. So did you look at how the impact of the sparsity of your light curve, like how that impacts your labelization?
I'm not sure if I understood the question. Are you saying that
I imagine you won't have the full light curve in effect. So how does that impact your labelization?
Yeah, so the way we're training right now, because we are using the MOA data, we have the full light curves, but it's true that when Roman will arrive, we won't have the full light curve. But one thing that happens, it's because the microlensing event can happen by the end of a season or by the beginning of the season. So we also have cases that we don't have the complete light curve. So this could be something that helps us to find these microlensing events in the sense that we have examples that we don't have the complete microlensing case in the light curve and we still can find it. So yeah, I don't know. Oh, this is frozen, but this is not frozen. Yeah, so I don't know if I answered the question, but I'm happy to chat about it.
Thank you.
Okay, great, thanks. Let's move to our next talk.